All right. So my name is Emmanuel, and today I'll be presenting our paper titled Private Graph Extraction via Feature Explanations. So this work is jointly done with Mandeep, Thorbin, and also Miga. All right. So in a typical graph learning task, you input your graph, and then you get a prediction from your after inputting the graph, you get the prediction. Now there are two schools of thought. Now in the first, which is privacy, interpretability, the goal is to understand the reason why a model is making a prediction. So which is in the direction of transparency, fairness, and trust. And the other school of thought is that of privacy, where you don't want to leak unintended information. So you try to protect everything as much as possible. And it has been shown that even your black box model can leak information. And this is, in fact, in the area of graphs and GNN models. So the goal of the study is to look at the interplay between these two conflicting views. One on the other, which is privacy, and the other one, which is interpretability. One wants to keep everything, and the other one wants to release everything. And that's the goal of this whole paper. So to kind of motivate this, in addition to your prediction, there is also explanation that is available. And for this, you can actually see this explanation 1011. It kind of talks about the importance of the features. So we are looking at the feature importance in this as the explanation. All right, and then the goal is to reconstruct the private graph, and that is the entire goal, giving the explanation and also some auxiliary information. I'll get into all this auxiliary information in a bit, but the goal is to be able to reconstruct this the private graph. All right, so what are the threat model? In fact, things that are available to the attacker. The first one is the explanation. The other one is the trained GNN model. The features and the labels, they could be optional depending on how the attacker wants to kind of use this information or whatever is available to the attacker. But entirely, the goal is to be able to predict the graph. All right. So for this, we use the feature explanations, and we use them from 6 explanation methods from 3 major classes: the gradient-based, the perturbation-based, and also the surrogate-based. So the attacks. For the attacks, we actually used from the simple similarity-based attacks to more complicated attacks based on graph structure learning. All right, so in the case in which only the explanation is available, we call this explain sim, and the goal is just to measure the distance between 2 explanation vectors. All right, by the way, the explanation vectors, they could be hard mask like this, or they could also be softmax, and we did exactly the same thing. All right, so if the distance is small, then the graph is constructed, just a basic thing. But in this context, we are looking at the distance between the explanation. So in more complicated scenarios where, in addition to the explanation, the features and also the labels are available, so we turn into a very interesting part, and we call this the graph structure stealing attack with explanation and features, GSEF for short. We have several variations of that. But in this architecture, there are actually 2 major parts. So the first part is this generator. All right, so this generator kind of generates the adjacency matrix, and there's the other part, which is the self-supervision. And the reason for the self-supervision is because there's something called edge starvation, which I'll be getting to in a couple of minutes. All right, so I'll be explaining each of the components, and I'll start with this generator. So the generator, what it does is it just kind of generates the adjacency matrix, which is the graph you're trying to construct. But then we use a fully parameterized adjacency matrix, meaning as the training progresses, then this kind of learn the weight, and then hopefully gives us the adjacency matrix we are trying to reconstruct. All right, and of course the normalizer is to make sure that this the adjacency matrix is not like negative and also symmetric. And for this self-supervision, we use the denoising autoencoder. And the reason for this is normally in graphs, there are cases in which your node might not be connected to any of the nodes that have labels. And you know how graph and GNN works. It uses the aggregation of your neighbor to actually label you. All right. So in this case, what happens is eventually, if we don't have this, let's say this self-supervision, what happens is the initial weight or the weight that was added in this that was generated will still remain the same, and that's the essence of this. So it just add noise and then try to reconstruct that. So we have three loss functions, and the first one is the one from you predicting the noisy version of your features, the noisy version of your explanation, and of course the downstream task. So it's more like a multitask approach. And lastly, you combine the adjacency together. And by combining the adjacency together, you take the adjacency that you have from your features and then that of the explanation, and of course you normalize it, and that is the final graph. Okay, so what are the variants? I'll just run through each of these. So there's one we call GSEF concat. It's just so at the input stage you already concatenate your explanations and also your features together, and then you do the entire thing. The same thing with the multiplication. You just multiply elements wise. And lastly, the GSE, which is you only have the explanations. You don't have any information about the features, and then you have that. All right. So what are the baselines? We actually compared with several state-of-the-art baselines, like this link-stealing attack, the graph MI, which is a white box attack, and SLAPS, which is a graph structure learning approach. And we used three data sets. Of course, we used additional 3 data sets as well. And in explanation, they always use 2 metrics, which is the fidelity and also the sparsity. So fidelity measures how well your explanation is faithful to your model. And the sparsity is, the definition is that you want your explanation to be as sparse as possible. You don't want everybody to, you don't want every of your vector to be ones, because that just means that all the features are important, which is what you don't want. All right. So what then are the results? So what we actually see here is that the explanations encode more information about the underlying graph structure. It encodes more information about the underlying graph structure. I hope I'm not too fast, or it's good? Okay, perfect. All right, so, and if you can see from this feature similarity, which also use the distance, we can see that in most cases, so the feature similarity at the dashed lines, we can see that this explain sim kind of performs better on most of this, on most of the explanation method. The same thing with this, which is in the fact of the GSEF. So when you try to reconstruct the graph with your explanation, we can see that it leads to better reconstruction of the private graph rather than just using the graph structure linear approach, which is SLAPS in this case. All right, just to kind of give you a quick snapshot of the beautiful, of this beautiful result, we can see that in most cases, depending on the way you combine the explanation, it really goes a long way as to whether you can reconstruct back your graph or not. All right. So we can see from this that the GSEF kind of performs very well compared to the other ones. But there's something about this Bitcoin data set. So one thing we figured out is, so this Bitcoin data set, there's no correlation, much correlation between the model and also the nodes, like the nodes, sorry, the nodes and the links, I mean. So there's no much correlation, and that's why the attack seems not to be successful. All right. So what then are the differences between the privacy leakage of all of this explanation method? So what we figured out is that GNN Explainer, I'm sure if you're in graphs, you actually know this big name, GNN Explainer. So there's low sparsity. So low sparsity meaning there is no distinguishing factors, distinguishing factors between the features and also the explanation. Therefore, you cannot extract as much information as possible. And also the same thing with GraphLime. It's not so faithful to the model. All right, and because GraphLime uses this surrogate model based on HSIC lasso to predict, to give the explanations for the model. But what we figured out is explanations in which are very loyal to the model, and those that have good sparsity, they kind of leak more information. Now, the only surprising thing, or one of the major surprising thing in this whole research is that we figured that the gradient-based method is not faithful at all right, to the model. And it also, there's so much of bunch of ones. So it's actually just telling us that most of these features are very important, okay? All right, 3 minutes, that's beautiful. Okay, and this is something that we figured that it could be because of the sensitivity of the input to the change. for every little change, then the gradient-based approach changes. So we also define something called the adversary advantage, which is quantified by the performance on a downstream task. So meaning that, assuming that you have a model, and then you want to kind of just use it on the downstream task after reconstructing the private graph. And one intuitive understanding of this is that, assuming you have a graph with features, and of course the graph, and then you train a GNN model, and your output is someone having cancer, and then you just use the explanation alone. They will probably give you about the same prediction for the same person. So if you just take the explanation alone, they will be about the same. And that's one of this notion of the advantage. And what we see here itself is that if it is closer to this graph structure learning approach, then it means that the attacker has the true features. However, if it's close to max, then which is max meaning that the attacker has both the features and the true adjacency. And we know that this is quite high in terms of imagine you're just using the explanation alone and you're able to, in fact, it is as though you have the true features and the true adjacency. And one other thing we figured out is that whether you have the ground truth or not, as long as you have access, the black box access to the model, there's no much significant difference. And lastly, to the defenses. So we used from the notion of randomized response, and we flip each of the beats. Yep, we flip each of this beat of the explanation. And then based on this probability, so it's based on the privacy budget. And of course, we also show that we satisfy epsilon differential privacy. And what we see is, of course, it really reduces the attack drastically, but there's a caveat. So this is the part in which it's a lot interesting. We can see the value from the fidelity, which is very good, meaning it's still very faithful to the model. But if you look at the sparsity is still very high. And I remember I was discussing with someone this morning about that. So, it is still acceptable considering if you look at GNN Explainer, which has no privacy guarantee, but at the same time, it would be good to kind of reduce this. And we also figured that we check the intersection. So intersection is the percentage of one bit that is retained from the original explanation. And indeed, we see that in most cases, the original explanation still holds, for instance, 75% of the time. All right, so the key takeaways are this. We can actually reconstruct the private graph over 90% of the time. And also, the strength of the attacks is based on the choice of the explanation method and how you actually combine that. All right, thank you very much. And we have a code available, and I'm open for questions. Thank you.
Thank you so much, Emmanuel. We have one technical question on Zulip, for which we will ask you to keep your computer plugged in. So okay. on slide 20, could you
slide 20?
Slide 20, yeah.
Okay. Ooh.
Almost there.
All right. 20?
Yeah.
Oh, sorry. 20. Yes, please.
So the question is, can you indeed just add these losses without rescaling the component losses?
Can we what?
Add the losses.
Yeah, so very good. So the reason why we added losses is, of course, this is experimentally shown. Yes, it is. We could actually scale, but what we figured out is it's better for them to be uniform, then we can be able to reconstruct the private graph effectively. Because if we scale one, then that means one can be dominant on the other, and we don't want that. So actually, it doesn't lead to a good reconstruction. Yeah, that's why we added it. Yeah.
Okay, thank you so much.
Yeah.
For more questions, Emmanuel will be able to answer them on Zulip or in person. So let's thank him again.
Thank you.